Hello everyone, this is a lab recording for lab 1 of ENL 270. This lab is on an introduction to some of the test equipment that we'll be using in the lab, both in the rest of this course, throughout the rest of your degree and throughout the rest of your professional career as well. The first thing we're going to do in this lab is have a look at the multimeter and DC power supplies. So the DC power supply we have here gives us a way of generating a constant controlled DC voltage. We can then use our multimeter here to probe some properties of our circuits, such as DC or AC currents and voltages, and resistances within our circuit as well. First thing we're going to do in this lab is get a resistor. I have selected this one here as an example. You'll find resistors in the green boxes at the lab benches, or if there are none in there, you can get one from one of the TAs in the lab. It doesn't matter which resistor you select for this lab. We're using this just as a demonstration instead. You can then identify the resistance of this resistor in one of two ways. One is by looking at the colored bands on the resistor. They encode the resistance and tolerance of the resistor, and you can use a color chart such as the one in the red folders, or there are many available online, to decipher or decode these bands and determine what the resistance of this resistor is. The second way you can do it is by using a multimeter, such as this one here. What we can do is get a couple of cables to connect the multimeter. What we want for this are banana to alligator cables. So this has a banana end connector on one end, which looks like this, and an alligator clip on the other end, which looks like that. To measure the resistance of a resistor, such as this one, we want to use these two ports on the multimeter here. The black one is our common or ground port. We always want to be using that one. I'm going to plug this banana plug into there. To measure voltage, resistance, or to test a diode, we use the right-hand side terminal on this multimeter here. Note that it may be in a different location on different multimeters, but it will always be labeled. These two left-hand ones here are labeled with current markings, indicating they're for measuring currents. The right-hand one here is labeled with voltage, resistance, and diode to indicate its properties as well. So we connect in another banana to alligator clip cable in there. Note that it is worth following the color coding on these terminals. It is not strictly necessary for this to work. Electrically, the colors do not matter, but it makes it a lot easier when you're observing your circuits. When you go to grab a multimeter, you can say, oh, right, I know the black is connected to ground, the red is connected to my actual measurement port. We then hook the resistor into the alligator clips, open them up, clip it on the leads of the resistor, and then we turn the dial on the multimeter to the resistance range. You'll notice here there are a number of options on this multimeter. Different multimeters will work differently. Some will auto-range throughout the entire possible range. Others will auto-range within a set range, which is what this multimeter does. So we have to figure out which of these ranges is appropriate for this resistance. So if I turn this to the 20 mega ohm range, you see we get 0 on the multimeter, which indicates that either this is 0 resistance, or more likely, the resistance is far smaller than the hundreds, tens to hundreds of mega ohms range, and so we can't measure it. So then we can turn the range down to the 2 mega ohm range. We see we start to get a measurement, and we keep ticking down until we get the most accurate measurement possible. Currently, I have this set on the 20 kilo ohm range. This is for the sort of low digits to tens of kilo ohms, maybe to the low hundreds. If I go down to the 2 kilo ohm range, you'll see at a 1 dot. And that indicates that what I'm measuring is larger than what this range can represent. So this value I've selected here is too small. So then I can tick up to the next one and see what I get. In this case, I get 4.66. We're measuring in the kilo ohms range. So that is 4.66 kilo ohms. And this is rated as a 4.7 kilo ohm resistor. So that matches what we expect observing the color bands. Note that while this says 20 kilo ohms on the dial here, that doesn't mean this is multiplied by 10 or anything like that. The 20 refers to the range we can measure within. It's the kilo ohms that matters for what we're measuring here. So 4.66 kilo ohms. Okay, so now that we've measured our resistor, I will disconnect it from the multimeter, turn the multimeter off. Always make sure you turn the multimeter off once you've finished using it, otherwise you will drain the battery in it. The next thing we want to do is connect up our DC power supply In the lab sheet, there is a circuit shown. What we want to do is connect 10 volts across this resistor and measure the current flowing through the resistor. We can then compare that to our calculation of the current flowing through the resistor and make sure we get the same consistent result. So the first thing we want to do is set up our power supply. I like to do this before I plug anything into the power supply itself. On these ones in this lab, we first of all turn them on. The power switch at the bottom there. And you'll see there are two sides to this power supply. This means we can have a dual power supply, which we will use in later labs. For this lab, we're only going to use a single side of this power supply, so I'm only going to show one of those. It doesn't matter which side you use if you're using a single power supply, they're both equivalent. Different power supplies will behave differently. This has two independent power supplies. Other ones will let you do what's called slaving them together in series or parallel so that you can get higher voltages or currents. But these are two independent power supplies. Okay, we then have two settings on this power supply, the voltage and the current limit. Firstly, I'm going to set the voltage. We want that to be set to 10 volts. So I'm going to turn the dial here. There are two dials on this power supply, coarse and fine. Coarse is for doing rapid adjustments, set to 10, and we can use the fine dial for small adjustments, like that. Now it is set to 10 volts, which is what the readout here is showing. The other thing we always want to do is set a current limit on the power supply. And this limits the maximum amount of current the power supply can provide from its outputs. This does not set the actual current that will be drawn, however. That depends upon the voltage set and the impedance of the circuit we're working with. This just sets the maximum amount of current. And that's to stop us accidentally blowing anything up. So if in our circuit we had a short circuit somewhere and we had no current limit, we will in theory get an infinite amount of current. In practice there will be some limit on it, but without setting that limit appropriately, that could be quite a large amount of current, and that could damage or destroy devices in our circuit. So we always want to have a current limit set. What you want to set that to depends upon what you're working with, what you're doing. In these labs we're going to be setting a consistent limit of 100 milliamps or 0.1 amps. And that will be more than sufficient for the labs we do in this course. So I have used the current dial here to turn that current limit down to 0.1 amps. I currently have nothing connected to the outputs of this power supply, so I can turn it on quite happily. To enable the output of this power supply, we also need to press this button here. You'll see it's got the label on above it. When I press that, this light goes red, indicating the output is on. So this is now supplying current. You'll notice when I press that, the current shown here drops to 0. This is roughly showing you how much current is being drawn at the moment. Do not change the current limit when the output is on. It will not show you what the current limit is, only how much current is being drawn. Similarly, I don't recommend changing the voltage here if you can avoid it. Only change these things with the output turned off. Otherwise, you'll end up with currents and voltages you don't expect, and you will probably destroy things in your circuit. Okay, now that our power supply is set up, what we want to do is grab some more cables to connect our power supply to our resistor. What I'm going to do first of all is grab a banana to banana jumper or wire like this, and I'm going to use this to connect the black negative terminal of this power supply into the earth connection on this power supply, which is on the right hand side over here. For this lab, this isn't strictly necessary. With a single power supply, using the positive terminal referenced to the negative is fine. It won't make a difference. But this is a good habit to get into of earthing your negative reference. Otherwise, if you're using multiple power supplies and you don't have a common reference, they will have different voltages between each other. So by connecting the negative terminal to earth, we ensure that all of these are referenced to earth. So it's a voltage with respect to earth. So it's a good habit to get into. As again, using a single power supply, it doesn't actually matter. It won't make a difference for this lab. You'll notice that the banana cables I'm using here have an empty slot here, so I can piggyback in a second banana plug onto this one, which is what we're going to do. So I'm going to take another, this time a banana to alligator clip, and connect that in to the end of that first banana plug there. I'm going to take another one and connect that to the positive supply. So now I have a positive lead and a negative lead. I'm then going to hook these onto either side of the resistor, again using the alligator clips. And I'm going to leave a bit of space on the end of the lead so I can also connect the multimeter. So I'm going to connect these alligator clips reasonably close to the body of the resistor. Don't clamp onto the body of the resistor itself though, it is insulated and will not conduct. Okay, so now I have this connected up. If I turn the power supply on, current will flow through the resistor. Nothing has gone wrong, as we expect. Our voltage is set correctly. Our current limit will prevent anything bad from happening. But we don't know what's actually happening. We have no measurement here. So I'm going to turn the output off. Again, I generally recommend turning the output off when you go to change your probing setup of a circuit. If you're just moving a probe from one point to another, you can usually leave the circuit on, but if you're changing a bunch of connections, just turn the power supply off. It's just a bit safer. Okay, so I'm going to then take the leads from the multimeter and connect them on either side of the resistor as well. And we're going to observe polarity here. So I'm going to connect the ground or negative lead of the multimeter to the ground or negative lead from the power supply, and similarly for the positive leads. Because we're measuring a DC source, it won't matter which way around we do this too much. We'll just get a negative sign instead of our expected positive sign if we connect it backwards. But to make life simpler and easier, it's generally worth following the same polarity unless you have a good reason not to. So now I have the power supply connected across the resistor and the multimeter measuring across the resistor as well. I can then turn the power supply on, and I can measure the current across this resistor, the voltage across this resistor, which is the first thing you'll need to measure here. So I turn the dial on the multimeter to the DC voltage measurement side, again to the appropriate range I expect. So if I turn this to the sort of 2 volt range, it's just a little bit too small. If I turn it to the 20 volt range, I'll get a decent measurement. Here I can see I'm getting almost exactly 10 volts across the resistor. In fact, I'm getting 10.01 volts. Which is close enough. I could adjust that using the fine voltage dial if I want to. Small measurements like this can be okay if it's measured or being instrumented. Again, generally I avoid changing these while the circuit is live. So I'm getting 10 volts across this resistor. You should be getting close to 10 volts as well. It shouldn't be sort of 9 or 11 volts. If it's sort of 9.8, 9.9 or 10.1, 10.2, that'll be close enough for this lab. What matters here is that we're consistent with our measurements and calculations. Okay, so I have now measured 10 volts across this resistor. We can then, as the next task in the lab states, calculate the current flowing through the resistor using Ohm's law. So we know the voltage, we know the resistance, so we can calculate the current. Okay, once you've calculated the current, we can then turn the power supply off and set this up to measure the current flowing through the resistor, which takes a small change in our test setup here. So I'm going to turn the multimeter off. What we then want to do is change how we've connected our multimeter into the circuit. So I'm going to disconnect that from the resistor and explain what we need to do. So we were just measuring the voltage across this resistor, so we're measuring either side of it. We now want to measure the current flowing through the resistor, which means we need to be measuring in series. Measuring the voltage, we measure in parallel across our component. To measure the current, we need to be in series, measuring effectively through our component. That means we're going to need to jump in between somewhere the power supply and the resistor. In this circuit, it won't matter where we do that. We only have a single component. In other circuits, it will matter where you do that, because that will determine which current you're measuring in your circuit. So always just have a quick think about where do you want to measure things based upon what you want to know. What I'm going to do here is disconnect the positive lead of the power supply, and I'm going to connect that to the positive lead of the multimeter. But firstly, I'm going to change the multimeter connection so that instead of measuring voltage, I'm going to disconnect that from the multimeter. We want to measure current. So we're going to change this to one of the 2 current ports here. If you don't do that and you start trying to measure currents, the multimeter will tend to beep at you or give you some kind of warning. So what I'm going to do is connect this into one of these 2 current ports here. There are 2 here, both have a different sensitivity and different fuse on them. we're expecting to measure a reasonably small current here. We've got 10 volts, 4.7 kilo ohms in this case, or whatever resistance you have in your case. So we don't expect to be measuring a high current, so I'm going to use the port labeled as milliamps and microamps. You'll note this multimeter has a 250 milliamp fuse on that port. The other current measuring port has a 10 amp fuse on it, so you can use that to measure larger currents. Note that some multimeters may have this larger one unfused, so just be a little bit careful, check what fuse exists if any, and just be a little bit careful what currents you're measuring. So I'm going to plug that into the current port there. Now if I switch to measuring a voltage, the multimeter will beep at me, warning that I have set this up to measure current, but I've turned the multimeter to measure voltage. If I try and do that, I'm probably going to just damage or destroy the multimeter. So just a little warning to you there. Okay. Now that I've hooked my multimeter up correctly, I'm going to connect the positive lead of the multimeter to the positive lead of the power supply. Like so. I'm then going to connect the negative lead of the multimeter to the unconnected side of the resistor. Like so. That way, current will flow out of the power supply, into the multimeter, out of the multimeter, across the resistor, and then back to the power supply's ground. You could equally do this on the low or negative side of the resistor and power supply. You would get the same result in this circuit. It doesn't matter which side of this resistor we hook up to. So we have now set up to measure current through the resistor. I like to set the multimeter up first. So let's get past all that beeping. Again, we want to measure DC current and our expected range. So I'm going to turn that down to the milliamp range and adjust as need be. I will then turn the output of the power supply on. And you see I am now measuring the current flowing through the resistor. And I'm measuring 2.12 milliamps. If I want to, I can try to change the range, see if I can get a more accurate measurement. In this case, this seems to be the most accurate measurement I can get. So this is measuring 2.12 milliamps. Note that while this display here on the multimeter may show 20 milliamps and then have underneath that 10 amps, that's just indicating the setting to have it on, or the limits of this larger current measurement port here. Because I'm using the milliamp and microamp measurement port, I will be measuring in milliamps. So I'm measuring 2.12 milliamps. So do this for your circuit, your resistor. Measure the voltage across it, calculate the current flowing through your resistor, and then measure the current flowing through your resistor and see if they agree or not, and comment on any differences you observe. Once you've done that, we can then turn the DC power supply off, turn the multimeter off, and disconnect all of the cables here. We can also put the multimeter away. We have finished with it for this lab. Disconnect our resistor, pop that back where you got it from, and disconnect and turn off the DC power supply. The next thing we're going to do is look at another really important piece of test equipment, which is the oscilloscope. So our DC power supply gives us the ability to generate DC voltages and currents, and our multimeter gives us a nice way of measuring DC voltages and currents. We can measure AC ones too, but we only get an RMS value. Our oscilloscope lets us measure things that are actually changing with time and gives us a much more accurate measurement of what's going on in more complex circuits. So what you're going to be doing is going through a training kit made by the people who supply these oscilloscopes, which will give you a few labs to go through learning how to use these oscilloscopes. So in the very first one, lab 1, we're going to be using the scaling settings on this oscilloscope and using that to measure the behavior of a sine wave. What we're going to need, first of all, are our oscilloscope probes. And these look like this here. They have on one end what's called a BNC connection, looks like this. On the other end, they will tend to have a double connection that looks like this: an alligator clip, which we use for our ground reference, and a shielded hook tip. This, we pull it back, there's a little spring inside here to protect this hook so it doesn't get damaged. If you really need to, you can pop this tip off to get a bearer, more of a probe type tip instead of a hook. If you do that, to make sure you slide the tip back on, press it back on afterwards. So we can use this hook here, or the probe inside of it, to measure our circuits. What we're going to do is take both of these probes, we need 2 of them, there should be 2 at each bench. We're going to turn the oscilloscope on, and while it's on, I'm going to hook up these oscilloscope probes as well. So let's move a little bit closer to the oscilloscope so you can see what's going on. To connect these to the oscilloscope, we take this BNC end here, and we connect to, and on these oscilloscopes, one of these 2 ports here. We call this a 2-channel oscilloscope because it has 2 separate channels we can use to make measurements. Other oscilloscopes will have more or fewer channels. To connect this to the oscilloscope, what we do is we take the BNC end and we slide it onto the port here. And you'll feel when it slides on, you'll need to rotate it a bit to line it up. Slide it all the way in, and then we rotate it to lock it in. So if you look at the side of this here, there's a little, you might be able to see that here, there's a little slide here for, there's a little detente, a little nub on the end of this port that slides in there, and then uses that to lock in. So you press it all the way in and then rotate to lock it in. So you shouldn't be able to pull it out easily. It shouldn't fall out. Don't yank on it too hard though. So we do this for both of these probes. You'll notice that these probes have little bands on them as color codes. So this has a yellow band, for example, and this has a red band on the probe and BNC connection. It doesn't matter which way around you connect these to the oscilloscope. That's just when you're probing your circuits, you can quickly figure out which channel corresponds to which probe. So I suggest using ones that have different bands on them if you're using more than one. Okay, so we've turned our oscilloscope on and we have connected our oscilloscope probes to our oscilloscope. Note that on the far left-hand side of the oscilloscope here, there is another connection here. This has the label Gen Out underneath it. We will use this in later labs for the wave generator of the oscilloscope. If you connect an oscilloscope probe to this, you won't be able to measure anything. Similarly, you cannot supply from this using an oscilloscope probe. So don't connect oscilloscope probes to this port here. They only go in these 2 here. Okay. What we're then going to do is take one of these oscilloscope probes, and we're going to connect the clip here to the little hook here labeled Demo 1, and the ground clip to the middle ground hook on the oscilloscope here. You'll see it's got a little ground marking underneath it. So pull that back and hook that through. We're going to do the same thing with the other oscilloscope probe. We're going to ground that and connect that to the one that's labeled Demo 2. It also has the label Probe Comp underneath it, which we'll look at in one of the later labs. Okay, so we've hooked both of those up. We're then, following the instructions, going to press the default setup button up on the right-hand side of the oscilloscope here. The training manual talks a bit about the layout of the front panel of the oscilloscope here, as well as the keys and what kind of terms we use for those. I've skipped over that, but I suggest you have a read of that first, just so you're familiar with the terminology we use, like soft keys, dials, front panel, those kinds of things. So what I'm going to do is press this default setup key here, and this just loads in a default consistent setup for the oscilloscope. The nice thing about this is it means that if someone else has been using the oscilloscope, we don't have to worry about what settings they've got on there, how they've configured it. We can just wipe all that back to a blank slate. Note that, of course, if you're in the middle of doing something, this will also wipe your setup as well. So just be a bit careful about that. Okay. We're then going to enable some signals this oscilloscope has, what it calls training signals. To do that, we are going to go and press the help key, as the instructions tell us to do, and then use that to find and set up the training signals. So the help key is near the what's called the channel 2 vertical controls. You can see vertical here. This is channel 2 with the number 2, and the help key is next to that. So you press the help key. You can see it comes up with a bit of information on the screen here. And we can see on the bottom here, one of these says training signals. Hopefully you can see that there. Underneath these are what we call the soft keys. We'll press the soft key that corresponds to training signals. It will tell us something about what these signals are and some setup for those. And we want to have training signal, in this case being sine, which it is. If we wanted to change that, we could press that key and then use this knob here and rotate through and select different signals here. So we go up to sine and then we press this to select. We then press output to turn that output on. Okay. Something to note, looking at this output though, is that when we look at the training instructions, the training signals, it'll tell us that we need to make sure we've got our probe set up in the correct probe setting. We're going to talk about that a bit later on this oscilloscope that's currently set as 10:1, which is what we want it to be. But we will talk about that in a bit, in a moment. Okay, now that we have this set up, we can see there's something on the screen, but we can't really see what's going on. We can't see if there's actually a signal there or not. So there are two things we can do at this point. One option, the sort of lazy option, is to press this button here labeled auto scale. What that will do is the oscilloscope will try to set the screen up so that it shows whatever is being measured. It can do this to some extent, but this does have its limitations. It can only really do this for signals that are large enough, so nothing too small in terms of voltage or current. Anything that is consistent, so a nice sine wave, for example. If you're dealing with bursts, digital communications, digital logic, things like that, auto scale will not be able to do that for you. So that is one option. That can be a nice way of getting an initial close-ish setup for a nice periodic signal, but you shouldn't overly rely on it. What we're going to do instead is to go through the instructions here and do this manually. And it's worth practicing doing this setup manually so that you can do this for either aperiodic signals or smaller signals or things where the auto scale just can't capture what we're looking at, which will happen quite a bit. So we have two options here of how to scale this. We have our vertical scale and our horizontal scale. The first thing we're going to do is change the vertical scale on the screen. That is how large this is. We are looking at what is displayed on channel 1, that's in yellow. You can see it also says 1 on the left hand side here with a number next to it, and 2 has no number there. And channel 1 is on because the channel 1 key is lit up, channel 2 is not lit up, so it's off. So we know we're looking at channel 1. To change the vertical scaling here, we use the large vertical dial here above channel 1. We turn that to change the scale. The scale is represented or stated at the top here as well. Currently it says 50 volts slash. We read that as 50 volts per div. On the screen you can see there are all these grid lines. At the moment this is set up with, vertically speaking, 50 volts between each grid line going up or down the screen. And that's quite a large scale. That's probably larger than what we're seeing. So we can turn this dial to change that scale. If I turn it once, that scale changes to 20 volts per division. And we can see there's a bit of something on the screen. If I keep turning that, I'll start to see more and more going on. What we want to do is, following the instructions, set this to be 500 millivolts per division, which is what we have up top here. If you set that any smaller, what we're seeing goes off the screen a bit. So that's about as accurate as we can get. Note that it is worth getting this reasonably accurate. What you can measure, the accuracy of how well you can measure something, is directly tied to how large it is on the screen, how clear it is. So the more of the screen you can make your signal take up, the clearer the measurement, the more accurate the measurement you'll get. Okay, so we fixed the vertical scale, but right now the horizontal scale is not very good either. Everything's kind of compressed in this one big blur. So we can change the horizontal time scale as well. So on the vertical axis, we have our voltage at the moment. On the horizontal scale, we have time. We can change that by using this horizontal dial up here. The large horizontal dial changes what we call the time base or the time scale. At the moment, that is set as 100 microseconds per division. So each vertical line is 100 microseconds apart in time. Following the instructions, we want to change that to be 50 nanoseconds per division. So we take this dial and we scale, turn it and turn it and turn it until we get to 50 nanoseconds per division, which we have now. And we can see we have a nice clear sine wave on the screen. Okay, so what you're observing now should be similar to what we have here. There's two other things we can do as well. We can change not just the scale on the screen, but we can also change where things are on the screen. We can move them around. We've, again, two options for that. We can move them horizontally and vertically. If I use this small dial here under the horizontal panel, I can move this signal left and right. This kind of corresponds to shifting it in time. So I turn this around, I can do what's called a delay. So you can see as I rotate this, a variable delay comes on screen telling me how far I've moved the signal to the left or the right. Okay, so I can move that around, and that can be useful for looking at different sections of a signal. If I then want to reset that, I set some delay up and I'm not sure where it is, I want to reset back to 0, I can just press this dial and that sets the delay back to 0. Similarly, I can move this up and down the screen vertically. That's quite useful for when you have more than one signal on the screen at the same time. You can move them so they're stacked up above each other rather than overlapping each other. I do that using the small dial underneath the appropriate channel. In this case, channel 1. I can use this small dial to move this voltage up or down. And I get a readout here telling me how far I move this up or down, how much offset I've applied. So I can move this up. I can even move this all the way off screen. And then, of course, we can't then observe what's going on. If I've moved this around, I want to reset it. Similarly to the horizontal case, I just press this and it resets that back to 0 voltage offset. So everything is centered in the screen. Okay. So now we know how to scale this oscilloscope vertically and horizontally and how to move signals around on the screen vertically and horizontally. The next thing we can do is start taking measurements from the oscilloscope. And then again, there are a few different ways of doing this. Following the guide manual here, the first thing we can do is estimate using the marks on the screen here, this grid line shown. So we can see there are these major grid lines, and if you look closely, you probably can't see it on camera, but if you look closely on the oscilloscope, you can see there are smaller subdivision ticks as well. And we can use those to actually make measurements. So we know at the moment that vertically speaking, there are 500 millivolts between each vertical division, and horizontally, there is 50 nanoseconds between each horizontal large grid line. So we can use those to measure the period and voltage of this waveform. When you're doing that, it pays to, if need be, move the signal around on screen a little bit, just so that what you're looking at lines up nicely with the grid lines and makes measuring this a bit easier. At the moment, this is quite nicely lined up horizontally. We have a nice crossing point here going through one of the vertical lines, and another one here more or less going through one of the vertical lines. So from that, we can then estimate the period of this waveform. For example, here I could say, okay, I have a crossing here, and another nice crossing here, and this is about half a period, and looks like there's about 2 divisions here. So 2 divisions with 50 nanoseconds per division means 100 nanoseconds for that half period, which means 200 nanoseconds for a full period. So that gives us a way of estimating the period. From that, we can obviously calculate what the frequency is as well. Similarly, we can also measure the voltage of the signal as well. In this case, we probably want to adjust our signal on screen. Ideally, we want at least one of these peaks or troughs to be aligned with one of these grid lines, and makes our measurement a bit simpler to do. So we can move this up and down vertically. For example, I can move the signal so that the trough is aligned this line here, and then I can count up grid lines to estimate what the actual voltage is, knowing that there's 500 millivolts between each of these large grid lines. And I can use the subdivision there and say, well, I know that's going to, in this case, be each of those be 100 millivolts. that's broken up into 5 intervals. So have a go at doing that to estimate what the peak-to-peak voltage of this waveform is. Remembering that peak-to-peak means literally the difference between each of these peaks, or the peak in the trough here. Okay. The other way we can take measurements on this oscilloscope, I'm just going to set this back to 0, is we can use the cursors. So our oscilloscope has cursors we can place on the screen, and we can move those around to take measurements. To do that, we first of all need to turn the cursors on. There's a button here. You'll notice there's a measurement section on the front panel. We press the cursors button. That brings up cursors on the screen. We can then move these cursors around and measure what the difference is between these cursors, and thus measure what we're seeing on the screen. So we need to, when we move these cursors around, first of all, determine which waveform we're looking at so we can measure the right thing. We're looking at source 1, which is channel 1, which is good. We also need to select which cursor to move around. At the moment, it has cursor X1 selected. So we'll start with that cursor. We then move that cursor around using this dial here next to cursors. So we can move that around on the screen. So what we want to do is use this X cursor to measure the period of this waveform. So as we move this around, this aligns with a different time. So I can move this to line up with a nice point on the waveform, and then find the matching point somewhere else on the waveform and use the other cursor. To change cursors, we use the soft key and the cursors button. In this case, we want to change from X1 to X2. I can do that by pressing the button repeatedly, or I can use the selection dial here. And then I press once I found the one I want. I can then move that other cursor around. Say over to here. And from that, I can measure the distance between these two cursors, and that's displayed on screen here. So as I move that around, that will display this as a delta X value. So it'll give you a particular time difference between those two cursors. So using these cursors, X1 and X2, have a go at measuring what the period of this waveform is, and thus what the frequency is. Okay. Similarly to those X cursors, we also have vertical ones, or Y cursors, and we can move these around to measure the voltage of this waveform. As you can see, the waveform is a slight amount of thickness on the screen. Generally speaking, with the cursors, if you want to measure a point, you put it kind of in the center of that point. That's the best measurement you can get. So using those two Y cursors, move those around and have a go at estimating what the peak-to-peak voltage of this waveform is using the cursors. Okay. The lab manual doesn't talk about this, but I will show you a third way of taking measurements on the oscilloscope. I'm just going to turn the cursors off so it's a bit clearer. The third option we have, if you look under the measurement menu here, is there is this button labeled MEAS, M-E-A-S. This brings up a menu of measurement options. Here we can select different types of measurements on each channel and add those so we can read out different things going on the oscilloscope. Again, this is a nice way of taking measurements. We have a nice simple signal such as a sine wave, but will not be that effective against other types of signals. So for something like a sine wave, a square wave, things like that, we can use this measurement menu just to take measurements for us automatically. If you're dealing with something more complicated though, you'll need to either use cursors or manually read it off the screen. It's worth being familiar and comfortable with manually reading off the screen as well. It can be very easy just to have a quick little look at the screen and go, is that signal what I expect to see? Yes or no? If it's not, has something gone wrong? Rather than having to set up all this measurement and go, oh, hang on, that doesn't seem right. So being able just to quickly eyeball the screen is a valuable skill to have. Okay. The next thing we're going to do is move on to lab 2 in the manual, and this is talking about oscilloscope triggering. So following the manual, we're going to reset this oscilloscope. I'm going to press default setup. The probe setup is still the same as before. Again, we're going to turn the sine wave training signal on using the same procedure as before and scale the channel 1 to be able to measure that signal. There we go. So seeing the same voltage scale and time base. Okay. So when the oscilloscope takes measurements, it does so using what's called a trigger. Basically, the oscilloscope needs to decide when to take a measurement of what is going on. It's measuring some continuous signal and needs to capture that so it can then process it and display it on the screen. And it needs to know when to do that. That is decided by using what's called the trigger. So we can see here on the top of the screen, there is a little orange triangle. And that shows us where in time our trigger location is. So at the moment it is triggering right in the middle on 0 time. We can adjust the trigger though as well. What we do is we adjust the voltage level of the trigger. So on the oscilloscope, on the front panel here, you'll see there is a button labeled trigger. We can turn this dial and it will change our trigger level. So if I turn that, you'll see a line appears on screen representing where our trigger is. As we scroll that up or down, you'll see the waveform moves to the left or the right. And that corresponds to the voltage level at which this trigger is taking a measurement. As we dial this up, it is measuring taking a measurement when the waveform of the voltage reaches that voltage of the trigger. So if I set that trigger up here at say 675 millivolts, the oscilloscope will then take a measurement when this waveform crosses 675 millivolts. That corresponds to measuring that at a different point in time for a periodic signal like this, which causes it to shift on the screen. We can do the same thing. We can take a measurement at a negative voltage as well if we want to as well. Okay. So following the instructions, what we're going to do is set the trigger level to exactly 500 millivolts. That is one division at the moment, the current setting. You can also see the trigger voltage as you change it is shown in the top right of the screen here. So let's dial that up to 500 millivolts. And then what we're going to do is look at the trigger menu. So you'll see there's a button here labeled trigger. We press that. That takes us to the trigger menu. And this is where we can change or look at the settings of how we are triggering the oscilloscope. At the moment, we are triggering on edges. So we're looking at our edge on the signal. It's triggering off of channel 1. And it's looking at a rising edge, which is what this little symbol here is showing. It's showing something going up with an arrow pointing up. If we want to, we can change that. So following the instructions, we can press this button and rotate this dial to change that to be a falling edge. If I press that to select it, we're now measuring on falling edges rather than rising edges. This can be useful for different types of waveforms. You can see now that by changing from a rising edge to a falling edge, the waveform has moved on the screen. We've effectively inverted it because we're looking at this waveform when it drops down, the voltage decreases rather than when it increases over our trigger threshold. Okay. The next thing we're going to do is increase our trigger voltage until it is larger than the waveform we're measuring. So we were instructed to set it to 1.5 volts. So let's dial that to 1.5 volts. Okay. At the moment, the scope is now doing what's called auto triggering, and we see quite a mess on screen. By default, the oscilloscope will be in what's called auto triggering mode. Basically, what happens is that it'll first of all check the trigger level against what's measuring and see if it can then take a measurement based upon that. If it can't find something, so in this case, if it can't find a falling edge of this sine wave that is crossing 1.5 volts, so the sine wave decreasing from above 1.5 volts down to below that. If it can't find that, it'll basically take a bit of a guess. It'll say, well, I haven't measured anything for a while. I'm just going to take a measurement now. And it does that. It tries to make a good guess when to do that, but it's more or less just taking a guess. It'll say, right, I'm going to start taking measurements every 10 nanoseconds or 50 milliseconds. And so when it does it, we tend to end it with a mess like this, quite a blurry signal. This is an indication to us that the oscilloscope triggering is not set up properly. So if you get this on an oscilloscope, that's a good indication that your triggering is not set up properly. Okay. What I'm going to do is press the trigger level knob to reset the trigger to be on the middle of the screen at 50%. When I do that, we go back to our nice waveform from before. Oops. So now we're back in triggering range again. Okay. Now what we want to do, following the instructions again, is to disconnect the channel 1 probe from the hook it's connected to. So I'm just going to disconnect that. And we can see our signal goes to a flat line, indicating 0 volts. So there's probably nothing there. Okay. What we're now going to do is change our oscilloscope from the auto triggering mode to what's known as normal triggering. So we can do that. We first of all hook this back up again to see what happens. So in auto triggering mode, which we're now, if we disconnect, the screen clears. When we disconnect, we reconnect, it takes a measurement again when we reconnect. We can change what triggering mode we're in if we press the button labeled mode/coupling. You'll see on the left hand side, it currently says mode is auto. If I press that, I can change that to normal triggering. If I do that at first, nothing seems to change. But if I now disconnect the oscilloscope probe again, like I did before, if I'm careful with it, you can see what we measure is the last thing that we captured on screen. In auto mode, if I change back to that, it's constantly taking measurements. And so it says, right, well, I'm measuring nothing, it's display nothing. But if we're in normal mode, it retains the last thing that was actually measured. So when the probe disconnects, nothing is hitting the trigger. There is no falling edge going down below 0 volts. So the oscilloscope in normal mode says, okay, well, I'm going to retain the last thing I had on screen. Okay, we can then change this trigger level up to 1.5 volts. As we do that, we see nothing changes again. There's been no update of the trigger, so in normal mode, nothing changes. Now, if I reconnect the probe back to the Demo 1 hook, you can see still nothing changes. Again, we're still using this normal triggering mode. No waveform has gone across the trigger threshold in the way we've specified. Remember, we have this set to a falling edge at 1.5 volts. So no waveform on channel 1 has gone from above 1.5 volts and gone through down below 1.5 volts. So nothing has occurred to make the trigger take a capture or take a measurement. So in normal trigger mode, nothing will happen. This will not update. So this can be quite useful if you want to avoid having things change. Maybe you're capturing a small burst of voltages, say from a digital signal, and then you don't want that to update. The auto triggering will just wipe off the screen. Normal triggering will retain that on the screen for you so you can actually see what's going on. It's called normal triggering because this used to be the normal way the oscilloscopes were triggered as opposed to being automatically triggered. So this is a bit of weird terminology there. Okay. So the lab manual has a bit of a question about why the default mode for the oscilloscope is auto trigger as opposed to normal trigger. Have a think about that based on what we have observed using auto and normal trigger. Remember, you can change back to auto trigger if you want to play around and see what's going on. Have a go at answering that question, and then we'll move on to the third lab section, which is on triggering on noisy signals. Okay. For lab 3, what we're going to do is first of all go back to our default setup. So again, just put everything back to a nice consistent state. Again, we're going to turn our training signal on, but this time rather than sine, we're going to select the one that's called sine with noise. We're going to enable that output. We're then going to scale the oscilloscope. Again, we're setting this to 500 millivolts per division vertically, but we're going to set this to 200 microseconds per division horizontally. We're looking at a different signal here, different frequency, different period. We need a different time base. Okay, so we're currently measuring the signal. As we can see, we get this weird, glitchy looking, duplicated, noisy thing. The problem is that what's happening here is that this is a sine wave, a single sine wave, like we had in the previous lab. But because it has noise on it, it keeps going up and down, up and down, up and down, and it keeps crossing the trigger again and again and again. And so in auto triggering mode, this means the oscilloscope keeps taking measurements at weird timings, and we end up getting this duplication of the signal on screen. Okay. What we can do is have a little zoom in and see what's going on and sort of verify that the oscilloscope is in fact triggering on the rising edge. So when we put this back to the default setup, this puts the oscilloscope back to auto mode on a rising edge. So if we zoom into 200 nanoseconds per division in our time base, it's a little hard to see what's going on. What we're really looking at is noise, but there is a slight tick up there, which is our rising edge we're triggering on. Okay. So let's zoom back out to where we were, 200 microseconds per. Okay. So most signals that we measure in reality contain some amount of noise. Perhaps not as much as what's shown in this demonstration here, perhaps more, but there will be noise on signals you measure. And that can be a problem when we're trying to probe things. We can end up with this kind of situation going on. On these oscilloscopes, there are a couple of ways we can deal with that. One option is using what's called the high frequency reject filter that's built into this oscilloscope. So if we press the mode coupling button, there is one of the options here is labeled HF reject, which is high frequency reject. So if we enable that, we press that, what that will do is it will basically filter out high frequency signals. And later in the course, we'll talk about active filters, their design, how they work, and how to think about those. You'll also encounter those when we talk about signals in other courses. For now, it's suffice to say that what this is doing is saying anything that's happening above a certain frequency, in this case 50 kilohertz, gets cut off or gets reduced. So it tries to reject anything that's happening at a certain high frequency or above a frequency. Okay. In these oscilloscopes, this filter is based at a 50 kilohertz cutoff. So anything above 50 kilohertz is going to get cut off. Anything a bit below 50 kilohertz will also get a little bit reduced as well. So just be careful with this. If you're measuring a noisy signal that is occurring at a frequency of above 50 kilohertz, say you're measuring some signal at 100 kilohertz, it's a noise. If you try and use this high frequency reject option, it'll also cut off your signal as well as the noise, because what you're measuring is above that cutoff frequency. So just be a bit careful with that. This is fine when you're measuring lower frequency signals, but higher frequency ones it won't work for. Okay. What we're going to do is look at a second option we have available to us. So we're going to turn off the high frequency reject option, and see we're going to press this one labeled noise reject. And what this does is applies a filter that's not based upon the frequency of the signal, but based upon the amplitude. It plays around with what's called the hysteresis. We'll again cover this in more detail, particularly when we talk about Schmitt triggers in a few weeks. For now, it suffices to say that what's happening is that when the voltage crosses the trigger threshold, it then has to fall a bit lower for it to trigger that threshold again by going above it. And so there's some little gap in there. We call that hysteresis. By pressing this noise reject button, we're increasing the size of that hysteresis. So we're saying that for another trigger to happen, the voltage has to go above our trigger, drop down some distance, and then come back up again. And that gives us a bit more resilience to noise. Okay. Finally, the instructions tell us to, again, turn the high frequency reject filter back on. So now we've got both high frequency reject filter and the noise rejection on, and we get a reasonably good signal. And there's one other thing we can do. If we press the acquire button on the front panel here, we can change from acquisition mode being normal to what's called averaging. And what this does is just uses a pretty simple moving average filter, effectively, to average the signal on the screen. By default, it will take 8 samples to average it. We can change that if we want to. And so this can be a nice way, again, of just removing noise from a signal. Bear in mind that averaging a signal has its own effects on the signal itself. If it's a periodic signal like a sine wave, we're generally okay. but if it's something aperiodic, we may run into problems. So just be aware of what effects that has. The last thing in this lab that we need to do is take some measurements again of the period, frequency, and peak-to-peak voltage of the waveform, using the same thing we did in the very first oscilloscope lab. So using the observing on the screen, using the cursors, or using the measurement menu I showed you as well. Okay, we're passing over lab 4. This talks about documenting and saving oscilloscope results. This talks about doing it with a USB key and doing different ways there. We have a different option we can use in the labs, and we'll talk about that when it comes time, when that becomes relevant. So we're going to skip over lab 4 and go to lab 5. Where we're going to talk about probe compensation. So have a read through what the lab manual has there. It talks a bit about our model of an oscilloscope probe in terms of the resistance and capacitance within the probe. Once you've had a read through of that section, following the instructions, we're going to connect both oscilloscope probes. I'm going to reset the oscilloscope and connect both probes to what's labeled probe comp or demo 2, which is the hook on the left-hand side here. We're then going to change the scaling on channel 1 to 1 volt per division. And we're going to change the time base as well to 200 microseconds per division. I'm going to reset the trigger. I'm also going to turn channel 2 on and change the voltage scale on that channel as well. To turn channel 2 on, press the button labeled 2. That will turn it on. We can see it's currently set to 5 volts per division. We want to set that to 1 volt per division as well. And we want to move that to the correct position on screen. So we're going to move these on screen using our vertical adjustment dials, so we have them both displayed at the same time. Okay. So what you should see right now are a couple of nice square waves. Most, if not all, oscilloscopes will have some sort of probe compensation signal that it produces. And the idea of this is it gives you a square wave with a known frequency and voltage so that you can test that your probes are both set up and working correctly. Ideally, what we should see are two square waves with very flat responses, very flat tops and bottoms. If you look closely at the ones here, you can see, and I'll exaggerate this in a moment, but you can see they actually have a slight curvature at the edges, which is what we don't want to see. So what we can do is take what's called a probe compensation tool, which is just a small screwdriver. You'll find a couple of options. This is one that we have. It's just a small flathead screwdriver. You may also come across ones that look like these, which have two ends, one with the flathead out and one with the flathead recessed within. So we can take our probe compensation tool, our screwdriver, and if you look on the oscilloscope probes at the BNC connection end, you'll see there's a little screw in each of those. And that screw adjusts a variable capacitor within the probes. So for channel 1, if I turn that dial, I can adjust what's known as the compensation of this waveform. I turn it one way, I see I start to get quite a distorted waveform. If I turn the other way, I get the opposite amount of distortion. Okay. So if I turn this up too far, like this, we say our waveform is overcompensated. Apply that to channel 2, see if I can get undercompensated one as well. So you'll sort of see here, this ticks under a little bit. We call that undercompensated. What we want to do if we're getting this kind of situation is just turn the screw until we get a nice flat waveform. Something about that. And that means that we've set our variable capacitor to be correct for the particular setup we have. It's worth testing this, doing this probe compensation every time you go to use an oscilloscope, so you can check that things are compensated correctly and also that the scaling is correct as well. We can see here, we can measure our voltage here. We should, on this oscilloscope, at least have 2.5 volts peak to peak. Different oscilloscopes will have different voltages there and different frequencies as well. So you have to check the manual for those. But you should get a particular voltage, peak to peak voltage and frequency as well. So again, that lets you just know that your test equipment is working before you go take a bunch of measurements with potentially faulty test equipment or things that need to be scaled. Okay. So always make sure you go through and do that compensation before you start using your probes. It's quick and easy to do, but it will just save you quite a bit of a headache. The last thing we want to look at in this lab is estimating what the actual compensation capacitance that we have is, or the required capacitance there. So going through the lab manual, it talks you through how to go about calculating the proper compensation for our probes here. So follow through the exercise and calculate what you expect the capacitance of this compensation capacitor to be. Once you've done that, we'll go to the last oscilloscope lab, lab 6 that we're doing here. This manual has a few other labs in there as well, which you're free to look at. They can be quite of interest, but we don't need them for this course, so we're not going to go through them here. The last lab we're going to look at is using the built-in wave function generator on the oscilloscope. So what we're going to do, first of all, is just disconnect all of our oscilloscope probes. We won't need them for this particular one. And we're going to set this back to our default setup. Remember, when you go to disconnect your oscilloscope probes, you need to unscrew and pull them out. What we're then going to do is we're going to take what's known as a BNC to BNC cable, which looks like this. So there's a BNC connector on both ends. And we're going to use that to connect the wave generator output of the oscilloscope back to one of the terminals to probe with. The instructions tell you to go and change the probe attenuation factor. I'm going to skip that for now so you can see what effect it has if we don't do that, and then we'll set that properly as the instructions tell us to. Okay. So we're going to take our BNC cable and connect at one end. We're going to connect the port labeled Gen out on the far left of our oscilloscopes. Again, push it in, rotate it, lock it in. And we're going to connect the other end into channel 1, the channel 1 input that we had our probe in before. Again, locking it in correctly. We're then going to turn the wave generator on. So you'll see on the front panel here, there's an option labeled Wave Gen down here. If I press that, it will turn on highlight blue, tell you that it is on and active. And then what we're going to do is go to the settings here, and press default wave gen. And this just cleans everything up to a default setting, again, in case someone has gone and changed things. In this case, it sets it to a 1 kHz 500 millivolt peak-to-peak sine wave. To turn that back on, I press the wave gen button again to turn the output on. So I'm also going to set the oscilloscope scale up as instructed, which is 100 millivolts per division and 100 microseconds per division. So I've set this up as instructed, but we can see that the waveform has gone way off the screen. We know this is a 500 millivolt peak-to-peak sine wave, so at 100 millivolt per division vertical voltage scaling, this should fit on the screen quite nicely, but it's not. And the reason for that is that we need to set the attenuation factor of the oscilloscope correctly. So if we look at one of our oscilloscope probes, you'll see on the front here, this has a little switch with two options, 1x and 10x. And this sets the probe's attenuation factor. Basically, if it's set to 10 times, it reduces the amplitude of the input voltage by a factor of 10. If it's set to 1x, it doesn't change it at all. This can be useful for looking at voltages that are quite large, relatively speaking. But we also need to tell the oscilloscope that we've changed that setting as well, because the oscilloscope doesn't know what that switch is on. Some oscilloscopes and some probes are a bit smarter about it, or have some active attenuation there, will automatically figure it out. Most of them are set manually though. If we look on the oscilloscope screen here, we can see when it says channels, it says DC for both channels in yellow and green, and they're both set at 10:1. So in other words, this assumes that our oscilloscope probe that we've connected is set to a 10 times attenuation. So it's saying, okay, what's coming is 10 times smaller, so I'm going to increase it by a factor of 10 to correct for that change. However, when we're using a direct connection like this BNC to BNC cable, there is no attenuation between these two. This is a 1-to-1 connection. If this is set to 10-to-1 and this is set to 1-to-1, what we're measuring on the screen is 10 times larger than it is in reality. So we need to change that. To do that, we can press the channel 1 option, go into this menu labeled probe. You'll see there's another option here that says probe 10-to-1. We press that and turn the dial. We can turn that down to 1-to-1. So that will set the correct scaling. I then need to readjust my vertical voltage scale because that automatically keeps pace with the probe scaling. So if I set that to 100 millivolts per division as instructed, now we're getting the sine wave we expected to get. So whenever you're connecting probes or cables to your oscilloscopes, just make sure you know what attenuation they're set to, what attenuation their oscilloscope is set to, and make sure they match. Otherwise, what you're measuring may be 10 times too large or too small. Okay. So now what we're going to do is have a look at some of the options of how we can change this generated waveform. At the moment, this is set to 1 kilohertz frequency. If I press this button here, I can then rotate this dial here to increase or decrease the frequency. Note that on these wave gens, we have a maximum frequency of 20 megahertz. So I can change that frequency. We can also change the amplitude. You press the amplitude key, you can dial that up or down to change the amplitude of the sine wave. We can also offset our sine wave, provide some constant DC offset. Press the offset button, turn that up or down, and they'll offset our waveform up or down. Note that you can see it also appearing to move horizontally on the screen as a result of the trigger level being in a different place relative to the offset. Okay. So the other thing we can do, of course, is change the type of waveform we have. At the moment, we have a sine wave. If we press the waveform sine key, we see there's a whole menu of options here. We can select, say, a square wave, a ramp, we can do pulses, and just do a DC signal, we can do noise. Those are all the options we have here. With the square wave selected, we can also change what's called the duty cycle of the square wave, which is the ratio of the positive to negative pulse width. So at the moment it's 50%, which means that this width here is the same as the width here. The positive side and the negative side are the same widths. If I increase the duty cycle, I'll get a greater positive width and a smaller negative width, and vice versa. If I decrease the duty cycle, I'll get a larger negative and a smaller positive width. Okay. So that is our wave generator. There are 2 more questions in the lab manual for the oscilloscope labs. One is about the maximum amplitude limit of our wave generator here. So have a play with that, turn the amplitude up and down, see what the limit you can get is. And there's finally a question about how we could potentially measure current instead of voltage. And there's a note that there are 2 main approaches we could use. So have a think about those. Have a chat with people in lab and the TAs if you need some assistance there. Okay. The last thing we're going to do in this lab, we finish with the oscilloscope lab manual now, is we're going to look at the other function generator we have in the lab. So if I adjust the camera slightly, you can see up here, this is usually on the benches, but I've pulled it down to make it easier to see. We have our lab benchtop function generator as well. So oscilloscope has a built-in one, and we have an external one as well. So we're going to also use this signal function generator. To connect that up, we're going to disconnect from the oscilloscope, turn the wave chain off, and I'm going to connect the BNC connection, one end in channel 1, the other to one of the outputs of the function generator. By default, I'm going to use the right-hand one, which is a 50 ohm impedance connection, which is what this cable is. So I'm going to connect into that. To turn this function generator on, there is a switch on the back of it. You'll have to fiddle around to find it a little bit, but it's on the back of the function generator. Okay. When you're connecting to the function generator, make sure, as before, if we're using a direct BNC to BNC connection, that your probe scaling is set to 1-to-1 on the oscilloscope. If it's 10-to-1, you're going to measure something 10 times larger than it actually is. Okay. Now what we're going to do is we're going to set a particular waveform on this function generator. We want a 1 kilohertz, 1 volt peak to peak sine wave. So there's a few options we need to set here. First option is the amplitude of the waveform. You can see on the function generator, there is a dial labeled amplitude. And we can see here at the moment, this is set to, hopefully you can see that, 2.8 volts peak to peak. If I turn this dial, I can increase or decrease that voltage. You can see at the moment though, I can only turn that down as low as 1.6 volts peak to peak. To get smaller than that, I need to use these attenuator buttons up here. And these change the scale or the range of this voltage. One by 20 decibels and the other by 40 decibels. Which, again, we'll cover that more when we talk about filters. For now, I think of that as just a larger or smaller scaling factor. So if I press the 20 dB attenuation, this now drops down to 0.16 volts peak to peak. I can then dial that back up to our desired 1 volt peak to peak. So that's our voltage scaling set. We want to set the frequency as well. You see there are a number of buttons up here for frequency range, and these give us the sort of range of frequencies we're operating within. So if we're in the 300 range, we can use this dial to adjust sort of low tens up to sort of higher hundreds, maybe 300-ish hertz. We want 1 kilohertz, so let's go into the single kilohertz frequency range, the one labeled 3 kilohertz, and set the dial to about 1 kilohertz. There we go. So that's about 1 kilohertz. We also want this to be a sine wave. At the moment, you can see there are 3 functions this can produce: a sine wave, a square wave, and a triangle wave. At the moment, this is set to a square wave, so I press the button instead to select a sine wave. The other thing I always like to check as well is to make sure there's no DC offset being applied at the moment. If you press the offset button here, you can see if there is or isn't one. At the moment, there's a 160 millivolt DC offset being applied. I can adjust that using the DC offset dial. So I'm going to turn that down to 0. And you'll feel as you turn that down, there's a little detente, little static point in the middle at 0. To change the scale back to showing the actual output voltage, I can press the peak to peak / RMS button. That will show me again 1 volt peak to peak. I'm then going to adjust the oscilloscope to observe that waveform. At the moment, you can see the vertical scale is off, so I'm going to turn that down a bit. So I've currently set it to 200 millivolts peak to peak. I'm going to adjust the vertical scale slightly, a horizontal scale slightly as well, so I can see more of the waveform. So I've set that to 200 microseconds per division. Okay. Then, following the instructions in the lab manual, rather than measuring with the cursors or the division on screen, we're going to use the measurement menu. So, following through that, we're going to press measurement. Make sure source 1 is selected, so we're measuring what's on channel 1. And we want to measure the frequency and the peak-to-peak voltage as well. Currently, these are set up on the oscilloscope. If we wanted to change those, we'd press the type button and use the dial to select what type of measurement we want. Let's say we wanted to know the DC RMS, for example. We then press the button to add that measurement. Okay, so from that, you should be able to measure the frequency and peak-to-peak voltage being produced by the function generator as well, and take note of those in your lab manual. So you should measure that from the function generator, what that's supposedly producing, and what the oscilloscope is measuring, and compare and contrast the two, and try and determine which is more accurate or which do you think is better if there is a difference between them. Okay. There's the last set of measurements for the lab. The last section of the lab is talking about uncertainties, and make sure you're aware of the fact that the equipment we're using has uncertainties within it. No lab equipment, no measurement device is perfect. They all have uncertainties. So follow through those exercises and have a think about what uncertainties are present in the lab and what uncertainties are present in the exercises posed to you. Once you finish that, make sure you submit the lab at this lab manual at the end for marking. That is all for lab 1.